I thank Tom for starting NDC. I want to thank Payman especially for leaving NDC and going to work for Endologix. It's because he did that I'm here to give this talk that he started. And I definitely want to thank Karthik for doing all the work and for staying back in Fremont and being basically the only one that's working right now. So we're going to talk about, this is a change of gears here. We're going to talk about like caveman sort of techniques for doing like actual practical fatigue analysis of medical devices, that we do every day, and some of the limitations that we face with the techniques that we have available to us and that are commonly used in commercial practice. Just a quick note, you can download a PDF of this. It's already online. I'll show you this link again at the end if you care to have a copy. So first I'm going to talk about what you're going to take away from this, hopefully. So there's a lot to cover. So lesson number 1, I'm giving you all the punchlines here. So for surrogate specimen tests, these diamond fatigue type samples, strain limit diagram points depend on FEA in order to relate displacement to strain. That's really not a learning point, but it's something that's important to understand. We'll just look at that quickly. Here was what kind of led us down this path. Small variations in our calibrations of FEA material data can result in some cases, surprisingly large changes to the results that we see, kind of frighteningly so, and we'll show you that. We wanted to look into why, where this was coming from, and the punchline here is all of your material property data matters, but some matter more than others, and the loading modulus or elastic austenite modulus matters a lot, and as does especially the difference in plateaus, stresses, upper plateau minus lower plateau. That really is a big driver when we look at strain amplitudes in particular. So another thing that we learned here is that very important to use multiple samples to calibrate your data. That's probably obvious, but we're going to kind of motivate why that is and what the impact of that can be. And then some other interesting information here. Again, it may be obvious, but basically when we do these diamond samples, we see not a single strain. We target a single strain amplitude and mean strain, but we have a whole variety of strains that exist in that sample, and the implications of that can be confusing in some cases, and we'll see why. And then finally, just to tie back to Ali's talk from yesterday and other talks on pre-strain, that's a dimension that we hadn't thought of before, really, when it comes to this type of analysis, that it seems like it really matters, and we'll see what the implications of that are. Oh, acknowledgements. I also wanted to thank Alan for kind of getting us here in the first place. I don't know if I should thank him or blame him, but this should look familiar to many of you. Strain limit diagram, we might also call it a Pelton diagram, where we look at different sorts of specimens at various mean strains and strain amplitudes, and we look at runouts and failures, and then try to draw a line like this. That it may look like this, or it may look like that, or however you want to draw it, but you set some threshold and some criteria. And the thing that it may not be obvious here is that when you're doing these diamond samples, every one of these points, how does it get there? How does it get onto this chart? We don't go to the Enstone or MTS, if you like, and program in a strain amplitude and mean strain. We have to do finite element analysis to figure out the displacements that we need to set where these points are. So what kind of behind this is that each one of these points has a source of error in it that comes from the FEA analysis. And again, just to highlight that point, there's lots of different ways that we can do testing to get these kind of results. Rotary bending, tensile tension tests, or these diamond samples or surrogate specimens, and each of them have their place. But very often for medical applications, we say, hey, you really need to use a surrogate specimen that represents the actual sort of material, process history, thermal history, etc. It's the most realistic, but it also has this kind of complication of needing FEA to get at the results. So we do these sorts of analyses to look at the displacements that we need to achieve in order to get certain strain characteristics. Not unfamiliar. Okay, so now how do we get that FEA? Well, obviously we need material property data, which means we need to do testing, and we get these uniaxial curves, and then we need to translate that data into a set of input parameters that will stick into Abacus. In this case, everything that I'm showing here is using the commercially available Abacus elastic plastic model. Okay, so variations in either your test data or how you get that calibration are going to impact your points. Okay, so that was the first point. So now here's where we really kind of went down the rabbit hole. Two test samples, the red pill and the blue pill here, right? Same composition, same spec that they meet. They happen to come from different suppliers. You know, they look pretty much the same, right? And if you were to do a calibration and I were to show you this, you'd say, yeah, okay, they look pretty much the same, not very different. The elastic modulus is equivalent. The plateaus are shifted a little bit. One is up, one is down. There's this martensite modulus shift a little bit there. So if we look at it in terms of numbers, percentages, maybe it starts to look a little bit more suspicious. You know, lower plateau is up 35%. The difference between upper and lower plateaus is shifted down 26%. You know, so this is basically the numbers. But here was the terrifying thing is when we ran the analysis with these two different models, the strain amplitude changed drastically that we were predicting here. All right, so for models that look like they were the same, we're getting differences. You know, these crazy differences. So 70%, something like that. So you look at that and you say, holy moly, you know, could these points have 70% of error in them? You know, that made us feel like this, like, whoa, what's going on? Okay, so small variations in this calibration result in large changes to strain. All right, why? Why is that? We got to dig into this. So basically, two categories of suspects here: the model, which is the sensitivity of your results to the parameters, the numbers that we type in there, and then number two, they're related to each other, obviously, is the data itself. Like, are the materials different? Are the curves different, or something? All right, so first we looked at the model, and we ran like 12, more than 12 actually, but 12 plus simulations. We picked one target mean strain amplitude, in this case 3 plus minus 1, and basically we held everything fixed except for these different inputs, right? We varied these modulus and the plateaus and so on and so forth, and then we looked at different outputs. I'm really just going to focus on the strain amplitude. Got a bunch of data. Again, I'm not going to dwell on this. You can look at it later and download it, but those are the input parameters, and here's the output parameters. And you know, and you can see what the changes are. So you can start to see here the way that I highlighted them. The orange ones are the ones that went up the most, and the green ones went down the most, and you start to get an idea of which ones are most sensitive. So we took those results and fit a model to those, just a linear regression type of thing, so that we could basically get an equation out that says here's a strain for this condition. Here's a strain amplitude that we predict on the basis of these input parameters. And you look at a little chart here, and it shows you again the upper plateau minus lower plateau has the strongest influence, and the elastic modulus for austenite has, you know, similar high impact. All right, so we have this. So there's your third learning point. Results are especially sensitive to the loading modulus and the difference in plateau height. But what does that really mean, right? I mean, we know what these relationships are, but how much should we expect these input parameters to vary in reality, in practice? All right, so we went back, right? So the first curves that I showed you were real. You know, those were two curves that we took, and it led us to some confusion. And then, you know, you do what you do, which is you go get more data, right? See if you figure out what's going on. So we did multiple tensile runs, which is normal that we would do anyway. But we did n equals 5 for these two different lots, and we looked at the data. And then I also I was going to ask for volunteers to repeat the calibration multiple times, but that's a really boring job, so I just volunteered to do it myself, which I wouldn't recommend. I did use the little plugin that's available within Abacus to do that. So anyway, nice way to spend an afternoon. So we got a total of 50 UMAP parameter sets, okay, that kind of are organized like this, two lots, the top and the bottom, let's say. And then we can look at the variability within samples. We can look at the variability within lots. Really what I'm focusing on for this is just the variability between the two lots, lot 1 and lot 2. Again, a bunch of statistics, which I won't bore you with. We'll put all these in the paper when we get that together. But the upshot of it is, you see these kind of some big numbers here, right? It's kind of the difference between lot 1 and lot 2 in terms of the martensite or the unloading modulus down 29%, the lower plateau down 26%. But the factors that really matter, which is the upper plateau, lower plateau, was just 2%, and the loading modulus was just like 6%. So though some of the differences were large when we did all the statistics and actually did all the stuff, the impact on strain amplitude was a lot less than we were initially concerned about. So, we don't, in this case, have this like wild variation. It's kind of a plus or minus 5%. That's in this case. And that made us feel like, oh, relax. Okay. But the point is still here, right? Which is, you gotta kind of do your homework on this stuff. I think it's pretty routine to do multiple tension tests. The thing that may be less routine is to do multiple calibrations on that. But it's probably worth considering. Okay, on to the next point. So here's where I want to just kind of highlight this fact, right? That when we go ahead and do these surrogate samples, we're going to populate a strain limit diagram. Let's say we're going to decide which points that we want to investigate, and we'll pick them and we'll put them on the chart here. And then we'll go do some FEA to figure out what displacements we need to do in order to achieve those. Pretty standard. But the point is, we don't have just one point in that sample. We have all of these points. And the reality is that right here, in this area where it has the target, that has the target that we're looking for, that's like a tiny little volume. It's a little speck, right? Compared to the vast majority of the volume is seeing like nothing, and then there's this distribution of points that sees kind of like everything in between. But in any case, you look at this and you say, well, what's the most critical point in this sample? It's like that point there at the upper right. It's pretty straightforward. We can look at other cases. In this case, 3 plus or minus 1. We see a very similar thing. 3 plus or minus 2.5. Everything is like very normal. 6 plus or minus 1. Okay, what is going on here, right? So now we're puzzled, right? Because we're trying to target this value, and if we kind of just said, look, we're going to look at the most critical point where we know it is, and we see this, we say, okay, good. But if you go and look at all the points in your model, you find out that, well, geez, you've got this other stuff going on there. In terms of, there's no way that you can get this without getting that. Okay, so that's like, what is going on here? It's very weird. So let's keep going, though, and forge ahead. So now let's look at 7 plus or minus 1/2. And, okay, all right, that's cool. No problem there. But let's look at 7 plus or minus 1. Okay, we didn't change much here. I'm going to point out 7 plus or minus 1/2. 7 plus or minus 1. And now, like, whoa, this is like my point cloud has exploded. And I have no idea what to make of this. So the point here is, for certain conditions, you kind of can't solve this, and it's design specific, related to the specimen design itself, right? So this, if you need to get that, you need to somehow redesign your specimen in order to achieve that. Okay, so this is the point. If these were the 11 conditions that I wanted to target, I'm not testing 11 conditions. I'm testing all of these conditions all over this entire map here. Okay, so just be aware of that. All right, so there's the point. We see a wide range of stress and strain, and some of these conditions can't actually be achieved. Last point now. All right, and here I'm going to call back to Ali's talk yesterday, where we looked at this pre-strain effect. This is where things get really, things are going to get a little bit speculative here. I'm warning you, because we're just starting to really understand this. But Ali showed data where we looked at this 2% mean strain condition and looked at different pre-strains, 6, 9, 10, 11, and we see this impact in strain amplitude. So now, if we're gonna develop a strain limit diagram for some device, and we're gonna do some surrogate thing, we're gonna apply the maximum strain that the device is expected to see, right? So the data that we're going to be generating is going to be, for that high line, for the top one there. All right, but what we need to realize is that we have these other effects, and they're not insubstantial. I mean, what we showed here is that it's more than a 2x difference from the top to the bottom there. All right, so now I'm going to get a little bit speculative and say I don't know really if I were to recalculate this fatigue threshold at different levels of pre-strain. I don't know exactly what it would be, but it would have this type of trend here, where as I go up in pre-strain, this limit is going to go higher. Okay, so bear with me and just let's believe that for a moment, if you like. All right, and let's see what the implications are to our point cloud and fatigue analysis. So, in our simple world that we were thinking about previously, we have this one line, and we have one of these nice little curves, not one of the point clouds that's exploding on us, but it's very clear what our most critical point is, very easy. But let's take these points and just split them up. I'm going to pull out the points and put them in like bins here for each level of pre-strain. So 0 to 2, 2 to 4, and so on. All right, and I'm drawing like an imaginary threshold line. I'm just making it up to make the point here. I don't know what it actually is. It's going to come back on. Hello? Perhaps. It's a little fidgety. Okay, it's back. I'm not touching anything. All right, so here, again, it's imaginary, just again to make the point, but we know that for each one of these levels of pre-strain, there's going to be a different threshold, right? If this kind of theory all holds together, and now I think hopefully you're going to see the point, which is that is no longer my most critical point. Maybe it's somewhere else now that I'm going to predict failure. So it's confusing, right? So here's the point is that pre-strain seems to matter, and we need to come up with some way to think about that when we're analyzing these fatigue problems. So we've got mean strain, we have strain amplitude, and we have pre-strain. Now it's 3 dimensions. I don't know if anybody remembers this episode when Homer went into like 3D, right? But this is like, whoa, there's something else here that is going on. All right, so this is where things get a little. If we had for the other room, we could turn on the disco ball because things are going to get strange. So mean strain, strain amplitude. This is the way that that's the way we're used to looking at this chart. And here I'm just throwing this data at you. These are all the different conditions that we looked at. Same as the chart that I showed you before. But now, let's see. This is going to work here. Okay, so now you can rotate this thing and look at it in terms of pre-strain versus strain amplitude. Right? You can rotate it again, if you like, and see that each mean strain is associated with a pre-strain. So just to be clear, what we're looking at here, this pre-strain number it's like the strain we just pulled the strain out from the analysis for each one of these elements to see what was the what was the pre-strain or that maximum strain that the device achieved when it was crimped or whatever. All right, so every one of these is in some XYZ 3-coordinate location. All right, and we just kind of go back and then look at this thing sort of spinning around here. Let's see, like that. Okay, so this is complicated. Can't tell you that I could know exactly what to make of this, but there's something here, right? There's something that we hadn't thought of before, and that we're still trying to digest. Okay, so there's a lot happening. All right, so conclusion from that bit of it, we're beginning to kind of have an understanding that this fatigue criticality depends on not just 2 parameters, but at least 3. And I think maybe for next time, but these may not even be the right parameters. I think there's a good argument that mean stress or maximum stress should come into play here somehow, and there's definitely more sophisticated algorithms that are out there for looking at fatigue, life, and prediction, and a lot of work to do in the industry to sort that kind of stuff out. So I don't know how many dimensions we need. If anybody has seen Interstellar, you know what I'm talking about here. This is like the Tesseract or something. So there's the link again. So would love to hear your feedback if you have any thoughts on this. Thank you.
Thank you. It's a very